Good afternoon, everybody. Welcome back to the session 2 of today's conference. The theme of this session is electromagnetic systems in research organization. The talk is going to be given by Mr. Harish Dixit from VCET Vasai. Mr. Dixit is working as an assistant professor in Vidyavardhini's College of Engineering and Technology Vasai and pursuing his PhD from VJTI Mumbai. He has completed his graduation from the University of Mumbai and MTech from VJTI. He is currently working on synthesis techniques for high power circulators with the LHCD team of IPR Gandhinagar. Mr. Dixit is going to give us a talk on high power RF and microwave systems. Mr. Dixit.
Good afternoon, everybody. Originally, Mr. Pramod Sharma from IPR was supposed to give this presentation, but he could not basically attend due to some unforeseen circumstances. So, on his behalf, I would be continuing with the presentation here. So, basically, I am here to talk about high power RF and microwave systems. Now, whenever we talk about high power RF and microwave systems, we hear things like waveguides and Ts and microwave tubes and such things. Essentially, in the academic curriculum, they have basically been reduced to one, let us say, a subject. Most of it is basically not given much of the importance. We know, okay, a magic tea looks like this. Not much of the consideration is going. Even much of the research in microwave area is towards antenna and printed circuits. But once we go towards high power areas, the substitutes to waveguide devices are basically very hard to find out. So in this presentation, my endeavor would basically be to present to you in what ways there are research opportunities with waveguide devices and how basically we can use it to our benefit. So as a case study, I would basically be taking an example of nuclear fusion and where Institute for Plasma Research is basically working on, and how they are basically using these waveguide devices for achieving plasma heating and everything. Now, essentially, let us see if we go to the energy scenario. We basically require a lot of electricity. We require a lot of energy. So, in general, any country's development is basically taken as the consumption of its electricity. So, if we have to reach the electricity consumption of developed countries, basically we have to increase our electricity production by about 5 to 6 times. So currently India uses the major part of electricity production is about thermal, and then we have hydroelectric with nuclear energy, with nuclear fission coming in later. Now, basically, if we talk about energy from nuclear reactions, we have two processes. One, we have nuclear fission, and one, we have nuclear fusion. In fission, and basically we split up an atom. It basically a heavy nucleus is split up into two nuclei, and in that process, an energy is released. So we require a heavy nuclei. We require uranium, thorium, such materials. As compared to that, in fusion, we try to fuse together two light nuclei, creating a heavy nuclei. In that process, we would release the energy. So, a lot of organizations are trying to basically achieve nuclear fusion. Now, what is this nuclear fusion? Nuclear fusion, as compared to fission, it probably can generate more energy. It is more. It requires only deuterium and tritium, which are comparatively easier and available as compared to uranium and thorium. So generally, fusion is we have two light nuclei like tritium and deuterium. They basically are going to combine together and form helium and basically give out energy. In theory, okay, fine, but in practice, when we are trying to force together two nuclei, the two nuclei will contain some electric charge. So Coulomb told us that if we have two electric charges, there would be a force of repulsion among them. So Q1, Q2 by 4 pi epsilon r square would be by which they will repel. So I am trying to basically bring them together, and there is some force of repulsion for that. So what I must do is I must basically bring them so near, probably less than 10 to the power minus 15 meters, such that after that the Coulomb's force weakens and the nuclear force of attraction basically will take over and they will fuse together. So essentially what I require is basically give enough energy to the particles such that they come very close to each other. I have to supply a lot of energy to the particles. So if I want to supply a lot of energy to the particles, one way to supply a lot of energy is basically increase the temperature. The average energy of the particle is basically empirical formula is 3 by 2 kT. So if I want to increase the kinetic energy of the particle, one can basically say you increase the temperature. So the moment I go on increasing the temperature, the kinetic energy of the particles would increase and I can basically fuse them together. So how much is that temperature? So if I want to fuse together two particles, the temperature which I would require is about 200 million degrees, which is about 8 to 10 times that of the sun. So what I would want is, if I want to generate electricity using fusion, you have a very high temperature. Essentially you are basically, as one physicist famously told, you are trying to put the sun in the box. The question is how we are going to build the box. So one basic strategy is you take these gases and you create such a scheme that your gases which are there would not touch the box itself, because the moment they touch the box, they would collide with it, they would lose their energy. So you don't allow those gases to touch the box at all. In other words, you create a magnetic field around it such that the magnetic field will act on the particles and they will remain confined within the particular box. So we know that the force is QVB according to that. So it will create a force on the the particles such that they would be confined within the box. So one such structure which can enable you to do this is a Tokamak structure. So this Tokamak is basically, you can see a toroid based structure here, and you have some magnetic fields running in the toroidal direction and some magnetic fields running in the direction perpendicular to that. So these are the poloidal directions. So a combination of both of them would essentially confine your particles within the Tokamak, thus not allowing it to reach the box. Now once I have confined the particle, I would now like to give enough energy to it. I would now like to heat it. So how we heat those particles? And to heat those particles, we basically use electromagnetic waves. We will basically launch electromagnetic waves into this Tokamak such that those electromagnetic waves will transfer their energy to the particles, thereby increasing the temperature and their kinetic energy. So generally 4 strategies of heating are used. One is the neutron beam injection, one is the ion cyclotron resonance heating, then we have the electron cyclotron resonance heating, and finally the lower hybrid current drive. All these 4 heating systems are used together to heat up my collection of gases such that they turn into the plasma state. I'll just give you a gist of those 4 methods. In neutron beam injection, just as the name suggests, we will shoot uncharged particles into the gases. So these uncharged particles, when we will shoot into the gases, they will collide with the atoms and the nuclei inside, thereby losing their energy and increasing the inside temperature. In the ion cyclotron resonance heating, we basically transfer the energy to the ions. So we give out the energy to the so-called ion cyclotron resonant frequency, which is about 40 to 55 megahertz. So and in the next one, that is the electron cyclotron resonance heating, what we do is we give energy to the electrons which then transfer it to the ions. So if I want to heat it using the electron cyclotron resonance heating, I would have to give it at a frequency of nearly about 170 gigahertz. So different heating strategies are used, all use different frequency ranges. So for all of them, I should be able to generate microwaves at those frequencies. Finally, we basically come to the low hybrid current drive. It is this system in which I will be elaborating about. The lower hybrid current drive is basically meant to heat up the plasma in the direction of plasma or the gas flow. For example, here, if we say the plasma current is in one particular direction, so I would like the lower hybrid wave to flow in this direction so as it would heat up the plasma current. So I would want only a unidirectional flow of the wave inside the toroid. I would not like a bidirectional flow of the wave inside. So if I want to basically go for a lower hybrid system, my requirement is the frequency for this is about 3.7 giga. The power levels can reach up to about 2 mega CW. So continuous wave 2 megawatt power I would have to give at about 3.7 gigahertz. So if I want to do that, so remembering those two things, the specifications of the LSCD system are, we want 3.7 gigahertz frequency, the power is 2 megawatt, and we will understand later what is all these things, the conventional grill and the 32 rows. I will basically elaborate it as we go ahead. Now the system at IPR for the LSCD system as IPR is as shown there. Now it is a very good system for understanding about the use of various microwave devices. We see the ET, the HT and everything, we basically see it in the books where they are actually used. It is a very interesting schematic here. So one can see here, these four green color, these are Klystron tubes. These tubes are used to generate high power. I want to generate high power. Solid state devices cannot do that. So you have these Klystron tubes used to deliver high power to it. Each of them basically delivers 500 kilowatt of it. So 4 tubes are there, so that becomes 2 megawatt of power. Now these tubes basically you can see deliver their power. This power is basically then split up. So you have a lot of splitters. And these splitters basically then give the power to an antenna which then delivers it to the toroid. Now, as I told you that in the LHCD system, we must have the flow of the wave in only one direction, not in many directions. So to enable this, we have a special type of antenna. We cannot go for a conventional horn antenna or something, because if we go for that, we would have a bidirectional flow of the wave. So we can see here, this type of an antenna is called as a Grille antenna. So there are 2 slots, each of them have 32 mini slots here. So one can see here a lot of small slots are there. So whatever is the input power is basically divided by those dividing networks, and each one of this slot is given a portion of the power. So basically your 2 megawatt is divided into 64, and this is and a portion of that is given to each of this. The reason this is done is basically to give each of the wave a different phase shift. One can see in this LSCD system, there is some phase shifters here. Now these phase shifters can be made up of a material to give some phase shift as the wave propagates inside. The reason we require this phase shift is because if one sees at this graph, see, we would want the power flow to go only in one direction, not in the other direction. So one can see this 0 is the midpoint, the positive values refer the preferred direction, the negative values are basically the non-preferred direction. So one can see that the effect that the phase difference between the power supplied to each and every grill has on the power going in the preferred and the non-preferred direction. If the phase difference between 2 consecutive grills are 60 degrees, we can see that the power going in the preferred direction is much more as compared to the power going in the non-preferred direction. As the phase difference is decreasing, we can see more or less equal flow of power. So therefore, we must give it an optimum phase shift such that the power flows in one direction only. So therefore, we have those phase shifters, and therefore we divide those power lines into about 64 parts before delivering to the grill antenna. So one can see this transmission line structure there, which is used to divide it. This is probably as high as about a 3-floor building. So this is basically then used to divide it, and this finally the output goes to the Grille antenna here. So the Klystrons used basically have a frequency of 3.7 gigahertz at a power flow of about 500 kilowatt. And one important thing is the VSWR that it can tolerate. It is about 1.2. So if the klystron, we are now delivering energy to the plasma. The plasma or the gas will basically continue to change its state. So the impedance seen by the klystron will keep on changing. So if I have a transmission line having some characteristic impedance Z0, the impedance is ZL. If ZL keeps on changing, there is going to be some reflection. These reflections would travel back and they would hit these klystrons. The moment it hits this klystron, there would be some VSWR here. The klystron cannot tolerate a VSWR of more than 1.2. So these reflections which come back, I would not like that reflections to hit the klystron. I would basically like those reflections to be diverted. So there we have these circulators. So we study academically that the circulators is a device which flows the power from 1 to 2. If I give anything from 2, the power goes to 3, and if I give anything at 3, the power goes to 1. So essentially 1 is where the klystron is, 2 is basically my plasma device. So whatever power I give from 1, it will go to the plasma. Now because of the changing plasma, something would be reflected back. Now the circulator, what it will do is, it will not allow that to go to 1, but that would come at 3, where I can have a dummy load, and that dummy load can then absorb the power. So this non-reciprocal performance is basically due to a non-reciprocal material inside, which is the ferrite. Now this is a schematic of the load. Basically what we have is, I want the power to be absorbed. So here we have an air waveguide. Then we have a water waveguide. Water is very lossy at high frequencies. So I can basically transfer the energy of this air to water, thereby heating the water. So I can have a flowing water. So we can transfer the heat to the flowing water here. And to basically match the impedances, here we see the brown color is a small lambda by 4 transformer. So we normally study this, a lambda by 4 transformer, that if Z1 is an impedance and Z3 is an impedance, then Z2 can be square root of Z1, Z3 at a length of lambda by 4. So this principle can basically be used to build the water load here. One can also see here the power supply system, which basically works at 11 kilowatt, and here we have a crowbar. So this crowbar switch, basically as Professor Ramchandran said in the morning, we must study about the lines and everything. This power supply system is very far away. So if I switch it, if I switch it off, the line will exhibit some capacitance. This capacitance can then cause harm to the klystron. So essentially we have this crowbar switch which would protect the klystron from the damage of the capacitor there. So the common challenges are basically arcing. Arcing is generally dielectric breakdown. I have a dielectric, you give a potential, the dielectric will break down. So common challenges are arcing. Probably polishing the inside of the waveguide structure can help us. Then thermal stress. Whenever you have high power, it would heat up the waveguide. When it heats up the waveguide, the heating will also cause mechanical stress. So here we can see a multi-physics approach. We only don't have electromagnetics, but along with electromagnetics, we have a thermal analysis of it. The thermal analysis then it will basically couple to the stress analysis also. So high power basically, even materials for high power are always a challenge. So a lot of research opportunity this basically presents. The RF windows, we basically pressurize the waveguides. So to pressurize the waveguides, we use some dielectric windows. So what material these dielectric windows are to be? How to manufacture these materials? They present a research opportunity for material scientists. Then we said that the phase is very important. If the phase is going to be very important, then we have to basically measure the phase so that if there is any change, we can then correct it. Now phase measurement is one of the most difficult things at high frequencies, because we should have a platform which works at that higher frequency. So designing a measurement system for phase. Moreover, designing a phase shifter is also quite complex. Along with it, magic tees and coupler, we normally studied in the books. They have some structure, but how to design them? how to get an optimum performance of that. More or less they are trial and error based or some optimization based. So a good research opportunity basically is presented here. So essentially, what is the conclusion of this is high frequency systems like waveguides, TEs, they provide ample research opportunities, especially in defense based and high power systems. So one can basically use a lot of work on this, so that in general it benefits a lot of people. Even these type of systems are used in treatment of a lot of cancerous diseases also. So it is quite an interesting field to basically work in. That is what I would like to close the presentation.
It's a wonderful talk. I would invite the audience to ask some questions if they have. Yeah, please go ahead.
What kind of skills sets or building technology to the student experiences to tackle such problems, cutting edge problems?
Basically, one has to first is one has to know electromagnetic. Along with that, it will always help you to know something about material science. Normally, in our syllabus, we don't deal much about materials, especially in electronics. So dealing with these materials, learning about what materials can be used, learning about how they can be machined and fabricated is always going to be a plus point for us.
Grille type antenna, is it a directive antenna or it has some built?
It is basically a directive antenna in one direction.